I have a function. I tried some experiment. I substituted a point. It's not 0. It's not a root. OK, I want to improve it. And using the tangent line, I get the formula which leads to the Newton method. And I'm really unhappy about the derivative here. So my question is, can I do something about the derivative while keeping the general idea? And actually, at the beginning of the course, we had a chapter on approximating derivatives. We needed to know the function at 2 points. That was enough. Now, as it happens, before I got to xk, there must have been another approximation, xk minus 1. So it means I actually know the function at 2 places, and therefore I can approximate the derivative at xk can be approximated by, and here is a triangle. Which way do I want to play it? It doesn't really make any difference. So let's start at xk minus fxk minus 1. That's the difference in value divided by difference in the horizontal direction. OK, I put it here into my formula, and something happens. The difference in values will be in the denominator, and the difference in x's will come to the top. So let's see. Xk minus, the function values will go down, and on the top there will be fxk times xk minus 1. And of course, if you want, you can switch the order, but since you are doing it both places, it gives you the same answer. OK, what next? Common denominator. That's a good idea. Common denominator. Well, let's see. I have to take xk and multiply it by this expression, and I'm going to break it into pieces. So xk, fxk, that's one of them. I'm multiplying out the bracket if you want. Then there will be minus xk, fxk minus 1. Then there will be minus fxk, xk. Minus minus yields plus. Fxk, xk minus 1. OK, there should be some cancelling. I remember from home. I've been looking at it, and I saw there is something fishy. What's x? There's no x. It's xk. Yeah, now it looks better. And I can see the cancelling. Here we go. Let's write it nicely. Which order do I prefer? OK, I'll start with that one. Fxk, xk minus 1. Minus fxk minus 1 xk. So you can see that the indices just switched. So that's nice. It's a nice picture to have. And in the denominator, I'm just subtracting f's without those x's. So it's a very nice formula. Aesthetics also plays a role in mathematics. If the formula is nice, we like it, and perhaps we remember it better. That's a nice formula. Do we need to remember it, by the way? The answer is no. I want you to know the bisection method and the Newton method, because they are like blueprints for everything that comes afterwards. This one, I don't like. I mean, I like the formula, but it's too complicated for my taste. So yeah, I'm not going to ask for the formula on the test. You won't have to do calculations by hand for this method on the test. It's a method, yeah. It moves us from xk and xk minus 1 to xk plus 1. So it's a new type of a method. Before, we went like that, but now we also need to know something about the past. Now, when you think about it logically, if you need to know the past also for the next step, how do you start it? And the answer is, well, you have to make 2 guesses. And then you can keep going. So that's a new method. It's called secant method. Why? Because I could derive exactly the same formula, but from a different story. Let's go back to our picture. I know my function at two distinct places. If I connect them by a secant line, I can ask for the intersection with the x-axis, and that would be xk plus 1. So the Newton method, I said that I would prefer the name tangent method for the Newton method. And that's exactly one of the reasons why I like to see that way. Newton method went by tangents. The secant method goes by secants. That's a nice coincidence, nice name. You can calculate the equation of this line and then find its intersection, just like we did for the Newton. We found the equation of the tangent line and find the intersection. You can do the same work for the secant line, and you would arrive at exactly this formula. So it's not really difficult, and it has a nice geometric interpretation. What do I do next? Well, I have the last 2 points. I connect, and so on. Here we go. There's the root. Okay? So the secant method, based on the picture, looks quite fast because, you know, I'm approaching the root really nicely. Let's make it official. Here we go. So the secant method for finding root, we have a function which is continuous. I don't need derivative. That's a big advantage. I start with 2 points, x0 and x1. And then I'm just following the formula. And for some reason, when I was typing it, I preferred to start here with xk minus 1. It's the same, yeah. And then there is a stopping condition. Because again, we have the same problem. How do we control the error? So the answer is we cannot control the error. So there is no error control. It's not a bracketing method. So everything that we said about the error regarding the Newton method, I mean the general points, they are still valid. We cannot really tell precisely what the error is, so we have to apply stopping conditions. When I look here, I can see that I'm suggesting 2 stopping conditions. The first stopping condition is the absolute difference. I'm looking at the difference of the last 2 approximations, and if it's small enough, I say, okay, that's enough. The second possibility is I'm going by the value. And we know that none of them is reliable, and we also know that we cannot do really better. So the same story. Unreliable. And again, the same story. Imagine, okay, Camel, let's try this one. Camel is quite bad for it as well, for the secant method, but this one is nice to see. If you are unlucky and you guess your 2 numbers here in this region, then the secant line will bring you here. And you have 2 values, you connect them, and the secant line brings you here. And you have secant line and so on, and you can see where it leads. You would go to infinity with your approximations. Not very nice. You will never get to this root. So essentially, the behavior, the general behavior of the secant method is very similar to the Newton method. Because after all, it's just an approximation of the Newton method. We have unreliability, we have no error control. How about the speed? Well, let's make some experiments. Let's go back to the very first problem, this cubic polynomial. Let me remind you, x cubed minus x minus 10. And for the bisection method, which is a bracketing method, we started with the interval 0, 5. Now, I will start with the same numbers for the secant method, although now it's not bracketing. These are just 2 numbers. Let's have a look at it. And we got to the root after 20 iterations. Why is it so slow? Well, let's have a look. Here are our x's. The first 2 guesses, 0 and 5. Then we go to 0 and then to 61. So again, it likes to travel, just like the Newton method. Then we went back to 0 and then to 11 and so on. It kept traveling and finally it settled down. So the secant method is also very sensitive to starting situation. That's life. But as I said, the actual number is not really that important. What we really care for is the rate of improvement. So I'm going to 10 to negative 7, and for that we need 21 iterations. And that's what we care about, this comparison. So you can see that the bisection improves slowly, Newton improves really fast, and secant is, yeah, it's not bad, quite fast. Let's talk a little bit about the sensitivity. Let's go back to the original tolerance, where we had how many? 20 iterations, that fits. And I'm going to change the starting points into, let's say, 1 and 3.5. Now, notice that these 2 points are on either side of the root. So that's an interesting situation. We have a root, and we start the secant method like that. So I wouldn't expect too much trouble. We will see. Yeah, nice. 8 iterations, which falls somewhere in between Newton and bisection. But as we can see, this doesn't really tell us much. One would say, okay, 8 iterations, it means that it's faster than bisection and slower than Newton, but it's not comparable because of the different starting position. You can see just small change in the initial 2 conditions, initial 2 numbers, and you get widely different behavior. So that's a slight disadvantage. Now, just out of curiosity, let's improve the precision here. And we get 9 iterations. So that's exactly the important observation, the rate of improvement. Okay? Let's have a look at some theorems. We have a function which is twice continuously differentiable. We don't actually need it for the secant method, but we need it if we want to analyze the error. So that's just a mathematical restriction. Now we have a sequence generated by the method which is convergent. We have to assume it because, as we saw, it may happen that we don't have any convergence. But if we have a convergent sequence produced by the secant method, then we get a comparison for the errors, which we can see here on the last line, and it shows us that it's a method of order alpha. If the root is simple, here we go again. For simple roots, it's a method of order alpha. What's alpha? Alpha is a very curious number. Just out of curiosity, the rate is about 1.6. So it really falls between Newton and the bisection. Bisection is linear, and Newton had rate 2 or order 2. Now, if you remember, there was a chart here which was comparing the behavior of errors for different formulas, for different orders. And there was a line where ek was raised to power 1.5. Now, I didn't want to use 1.6 because I couldn't do the calculations in my head, but 1.5, 1.6, they're pretty close. So that line in the chart, if you look in the video now back, that line is essentially telling us how the secant method behaves. It's quite fast, not as fast as Newton, but it's very fast. So that could be the end of the story for the secant method. But I'm not going to stop here yet. I'm going to talk about something really, really interesting. First of all, secant method is less flexible than Newton. Why? Because it's somehow inherently based on one-dimensional situation. You don't have a tangent line from 2 points in more dimensions. So it's hard to adjust it to more dimensional situations. In this respect, the Newton method is much more flexible. But on the other hand, the secant method can be faster. Now you may say, wait a minute, how can it be faster if it is a lower order? The problem is the order is artificial, the one that we defined, in a way. And second, it's not practical. Let me explain. How did we calculate the order of the bisection method? We split the interval in 2. What if I decide that one cycle of the bisection method, one iteration, means that I split in half and split in half and split in half? I simply take 3 stages of the regular bisection method and call them one stage of my new improved method. Then this new method will be faster, but it still will be the bisection method. Of course, it will be cheating, but how can you tell? So the order of a method as defined mathematically is actually not as transparent or not as unique as one would like. Of course, mathematicians don't cheat because they are really interested in knowing how methods behave. But the right measure of the speed is how much work you have to do for a certain improvement, which is a different story. Now, where is the work? Well, there is some service that you have to do. You have to run a cycle. You have to check on the conditions. You have to do some, perhaps some decision making in the bisection method. Do I choose the left or right? But it turns out that this is not the big problem. The real problem is function evaluation. This is what takes most work. So a practical point of view is slightly different. It asks, what is the improvement in precision for one evaluation of a function or a derivative of a function? It's about the same problem, if I have it. Now, let's have a look at the bisection. How many times do you have to substitute into a function for one step? And the answer is, well, actually, just one. You find the middle, which is a very simple algebraic operation, and then you substitute into a function. So for the bisection method, the mathematical order is 1, and the practical order is also 1. This practical order doesn't have an official name. That's my name for it. But it's a viewpoint which is really very useful. How about the secant method? Mathematical order is about 1.6. And by the way, 1.6, why such a strange number? I cannot give you a nice story about this number. Why it's exactly this number. But I look at the formula and I say, wait a minute, I've seen this formula before. You know what it is? It's the golden ratio. Isn't that amazing? You probably heard about golden ratio. It appears in nature in many situations. It appears in arts. It's one of the most important numbers in arts. It's found in quite many places. Depending on how you look at the world, you may feel that this number is very special. So for people who are of the esoteric band, the secant method is the right one, because the rate of convergence is the golden ratio. Wonderful. Anyway, let's go here. Secant method, that's the mathematical rate of convergence. How about the practical rate? How many times do you have to evaluate your function to get a new approximation? Well, you need fxk, that's one evaluation. You still have it. And this one you remember from the last time, because you already evaluated it in the previous step. So just one evaluation, which means that the practical rate is also 1.6. Let's have a look at the Newton method. Theoretical evaluation, 2. How about the practical one? How many times do you have to evaluate for Newton? xk minus fxk over f prime xk. You have to evaluate twice. So it actually means that one step in Newton, order 2, is in fact, from the practical point of view, represented by 2 steps. Each has one evaluation of f. Now, how does it work with the orders? How does it work with the orders? Let's call these steps not E, but let's say F. So the official Newton works like this. I'm going to drop the constant now. Whereas the unofficial step looks like this. We have Fk, and then there is some imaginary order. Let's call it Q for the second. And after I do Fk to Q, this makes the error of this intermediate stage. And then I apply another stage of the same type. And I get the final error. That's how the practical point of view sees it. I guess I can afford to put E here. So let's put E here. Now, these two procedures are in fact the same. This is the mathematical point of view, this is the practical point of view. So if we compare them, we can see that ek squared should be what? How much is this? This is ek to q squared. So q is square root of 2. So we can say that the practical point of view for Newton yields rate of convergence 1.4. So, if you are evaluating function, which really takes a lot of time to evaluate, I talked about this experimental work, then the secant will be actually running faster than Newton. Although the number of cycles will be larger for the secant method, the number of work will be smaller. You can also look at it this way. You have an error. If you use Newton, you get a new error, ek squared, which doubles the number of digits if you are close to the root, number of correct digits if you are close to the root. If you decide to do the secant method, you get ek to approximately 1.6, but you do it with just one evaluation of f. So by the time this calculation is complete, you still have time to make another step of the secant method. Measured by time, not by cycles, this is the same. So the secant method can actually make 2 steps, and the 2 steps mean that I'm taking ek to 1.6 and again to 1.6, so it's ek to 1.6 squared, and 1.6 squared is about 3, roughly. So the improvement in error is much better for secant when I measure it by, let's say, the time spent on the calculations. So that's interesting. There is a big difference between a mathematical notion of order and a practical point of view. From practical point of view, the secant method is better. It's faster. It also doesn't need derivatives, so it has big advantages from this point of view. But as I said, the Newton method has other advantages. And that's about it. These are the 3 basic methods for this course. I'm going to make another totally